Alright, in this section, we're going to talk about this thing called central limit theorem. This corresponds to book 7.1. Basically, from now on, what we'll try to do is try to connect sample and population. One of the first thing we talked about in this class is the difference between sample and population and how hard it is to get to population. So what we're trying to do is we're trying to use sample to somehow access our population, right? So now what we're trying to investigate is what happens when you take samples. How does it behave? What kind of distribution we will get when we take samples? So in order to inferential statistics, so again, inferential means educated guess, right? Educated guess. So what it is we're trying to use a sample, and it's a statistics. Statistics are just numbers we calculate from the sample to make inference or educated guess about population parameters. So in order to do that, we're going to work with the distribution of the sample means. You can interpret that as how does sample means behave. So let's look at the notations first. Mean of the sample means, oh, it says mean. So I know the mean is used with the notation mu, but it's not just mean, it's mean of the sample means. So I want to put a little x bar. So I know it sounds kind of weird. Mean of means, what does that mean? So what it is let's say I go out and survey 30 students and say, hey, how much did you spend on your textbook? And I calculate the average. Let's say you go out, survey 30 other people, and you ask them same question, hey, how much did you spend on textbook? And you calculated the average of those 30 numbers. Well, most likely the number that you calculated versus the number I calculated is not going to be exactly the same. Maybe it's close, but not the same, right? Somebody else goes out, survey another 30 students, their average is going to be not exactly the same. So what we're doing is we're calculating different sample means with x bars. So if we do a bunch of different surveys, we'll get a bunch of different x bars. So what is the mean of those x bars? That's denoted as mu with a little x bar next to it. Same, you can do standard deviation. Again, is sigma is standard deviation, but it's the standard deviation of sample means. So I'll put a little x bar there. So what it is that once we start taking sample and look at like sample means, then now we're looking at these type of distribution. So from now on, you'll see a lot more these type of notations because now we're start taking samples and looking at investigating their properties. So now we're looking at this standard deviation and this mean. All right, let's look at number 2. Suppose x represents the amount of screen time a student spends on their phone. Let's say n is 30. So basically we ask each person what their screen time is, and we survey 30 people, right? What does x bar represent? So that's my sample mean. Okay, we knew that before, sample mean. So if you survey 30 people, everyone's gonna have different time, screen time. You average them, that's your x bar. So which do you think is most likely? X is less than 1 or x bar is less than? So this is, there's a subtle difference. Here, I'm gonna highlight this bar thing on the top. It represents the sample mean, right? So the first part is asking if you pick one person, what's the probability that this person has less than 1 hour of screen time? 1 hour because this is one here. The second one, it looks pretty much the same, but there's x bar on top, so there's a subtle difference and makes a huge difference. This means when you survey 30 people, what's the probability that the average of those 30 people, their average is less than 1 hour of screen time, right? So even though they look the same, they're kind of same, but there's huge difference. The first one is only for one person, and the second one, because there's a bar on the top, it means that the average of 30 people having less than 1 hour screen time. So they're asking, which do you think is more likely, this or that? Well, the first one is unlikely, but maybe there's like somebody who never uses their phone. Maybe it's like once in a while you'll find this person, right? So maybe this is slightly possible. But the second one is like, how do you pick a group of 30 people that they all have such a small number, so their average is one? In this day and age, probably not possible. So I want to say the first one is more likely to finding one person who has small screen time. Okay, maybe somebody, but finding 30 random people, that's going to be almost impossible. So I want to say the first one is less likely. Okay, next we're going to investigate a little further into the distribution of the sample means. So once you start taking samples, what will happen? So first it says, what will be the shape of the distribution of the sample means? And how does it compare to the shape of the original random variable? What's the mean and the sample means, and how do they compare? And then standard deviation, how do they compare? So this theorem called central limit theorem, it kind of tells you the answer to these three questions. And for next 3-4 chapters, you're going to be using central limit theorem a lot. So this is a pretty important concept. So let's see. 3 conclusions of central limit theorem. The first conclusion is x bar, the sample means, are normally distributed if n is big enough. So what that means is that if you go out and survey different samples, the numbers you're going to gather, the sample means that we're going to gather, they're going to be slightly different. But it's not going to be just some random numbers. They're going to form some sort of normal distribution. The second part of the conclusion is the mu is equal to mu x bar. That means the mean of the original distribution which is the mu, is equal to the mean of sample means. I know there's a lot. Okay, basically the original population's mean and the mean of the sample means, they're going to be equal. The third one is standard deviation is going to be smaller. So sigma with under x bar is going to be sigma over square root of n. What that means is that n is a sample size. So maybe you're surveying 100 people. So square root of n will be square root of 100. So when you divide something by square root of 100 or square root of 30, if you're surveying 30 people, then the answer will come out to be a little smaller because you're dividing by a bigger number. So what that means is the standard deviation of all your sample means is going to be smaller than the original standard deviation. Again, standard deviation tells you how things are spread out. So the sample means the numbers are not going to spread out so much, right? So if I go take a sample, if you go take a sample, our answer is going to be different, but it's not going to be that different. Most likely we're going to have a very similar answer. This is what it says. So number 3, if you're given a random variable normal, then the next, if you look at the distribution of sample means, again, it's sample means, right? It's going to be also x bar. Now I'm going to put the bar on the top because that's a sample mean is distributed. It's also normal. Mu is the same, and the standard deviation is. So basically, when you in practice, what it basically says is when you start taking samples, the mean is going to basically stay the same, but your standard deviation will be smaller by dividing it by square root of n. All right, now look at number 4. A sample size that increases, the distribution of sample means, again, when n increases, that means the number on the bottom, the whole thing becomes smaller. The standard deviation becomes smaller for the distribution of sample means. That means it has less spread. That means it's narrower. So I'm going to say it's narrower. Number 5, according to the central limit theorem, mean of the sample mean is basically the same as the original population's mean. So it's the same as the population mean. So again, mean stays the same, standard deviation becomes smaller. And then third one, According to the central limit theorem, the standard deviation of the sample mean is less than the population. So that's basically the same thing as it has less spread. That means your distribution is narrower. So if you look at the first conclusion, it says n has to be big enough. So like how big is big enough? For this to be happen, we need to have at least 30 as a sample size. And in the next section, we're going to have to redefine it. But for now, generally speaking, if you have more than 30, then your distribution of sample means will approximately be normally distributed. All right, now let's look at number 8. This is unknown distribution, has the mean of 45. Okay, so that's mu is 45. And standard deviation is 8, so sigma is equal to 8. Sample of size n is 31 are drawn randomly from populations. Okay, they're trying to take samples. So already I'm thinking, okay, this has got to be some sort of central limit theorem question. Part A, find the probability that the sample mean is between 42 and 50. Again, I'm going to highlight sample mean. So we're not looking at one individual number, we're looking at like sample mean of 31 people. I want to find the probability the sample mean is between 42 and 50. Okay, so according to the central limit theorem, the distribution of the sample means is normal, so I'm going to draw a little normal distribution here. Mean is same as the original mean, which is 45, so I'm going to put mean here. Mu x bar is 45. And again, I'm going to go by 1, 2, 3 standard deviation, 1, 2, 3 standard deviation. Here, because we are looking at the sample mean, we're no longer able to use sigma is equal to 8. We have to kind of convert that according to the central limit theorem. So our new standard deviation is going to be 8 over square root of 31, because the sample size was a 31. If you calculate that out, I get 1.44 if I round up. So what that means is I'm going to mark this off by 1.44. Notice I'm not using 8 anymore. So 45 plus 1.44 will give you 46.44. So I'll keep adding 1.44 and then 47.88 and I get 49.32. And the other side I'll just keep subtracting 1.44. So that'll be 45 minus 1.44, so it's like 43.56, 42.12, and then 40.68. So the question was, the sample mean is between 42 and 50. Okay, so 42 is somewhere like here maybe, and 50 is over here somewhere, so this area. So I feel like it's a pretty good size here. So what I'll do is I'll calculate normal CDF. The lower bound is 42, the upper bound is 50, the mean was 45, and then again standard deviation is 8 over radical 31. So if I calculate this out, it will give you 0.981. It's about 98.1%. So as I kind of guess it's going to be it was pretty much 100%. So what that means is if you go out and survey 31 people, most likely you'll get the sample average between 42 and 50. Okay, so I'm going to have you pause and finish the rest of the worksheet.